Hello everyone, I'm making this presentation for ECE 542 Neural Networks and Deep Learning. Project is Early Detection of Osteoarthritis in Young Dogs and our group number is Group 52. The project members are Shonil Bhide, myself, that is Kaushal Mapsekar, and Varat Patwardhan. The project contacts were Dr. Masataka and Dr. Duncan from College of Veterinary Medicine. A problem statement is to use neural networks to detect osteoarthritis in young dogs by analyzing their walking and trotting pattern to diagnose osteoarthritis. So, what is osteoarthritis? Osteoarthritis is a degenerative joint disease that develops in dogs over a long period starting at a young age. It is commonly diagnosed after 8 years, and studies have shown that around 40% of young dogs have osteoarthritis. Now, why should we detect osteoarthritis early? Because clinical signs appear visually mild and are difficult to detect in young dogs. There are potential benefits if doctors treat osteoarthritis early, and presently there are no tools available for early detection. Clinical signs used by vets for diagnosis include the dog's stance, stride length, and swaying of hips. Why are we taking pressure data? Because center of pressure has been used to analyze gait changes associated with joint pain. Now let's take a look at our dataset. The dataset is provided to us by NC State's College of Veterinary Medicine. It contains data of various young dogs collected using a mat-like pressure sensor. Data gathered by walking dogs on pressure sensor can be processed using a software called TechScan. It generates .fsx files and uses sensor and video data for visualization, which is then downloaded as CSV files, which we have used for our project. There are three classes of dogs: normal or healthy dogs, dogs which show radiographical evidence of osteoarthritis but experience no pain, labeled as ROA, and dogs showing radiographical evidence of osteoarthritis along with clinical signs, labeled as COA1. The data used by us consists of 24 dogs, 8 dogs of each class for having balanced data, each dog having multiple walks recorded. Data is then split into train, validation, and test sets in the ratio 64%, 16%, and 20% respectively. Here we can see the visualization of data and process of extracting CSV files using TechScan. We can see the pause registered as a heat map of pressure values. Each paw is then detected by the software as left hind, left front, and right front, and then displayed graphically as pressure versus time graph. Here is a video where we can see how the pressure varies as the dog walks on the sensor. One of the files we get from TechScan is M file or movie file. It records pressure values on the sensor frame by frame, each frame of size 384 by 88. Another file we get is the G file or graph file, which contains percentage of force exerted by each leg on the sensor at each frame. It, it is calculated from pressure versus time graph. We chose to use this file to extract temporal features and detect differences in gait. Let's take a look at our model. We are the first ones to work on this problem, so there were no pre-existing or pre-trained models to refer. Hence, we built our own baseline to see how a simple classification model like random forest performs on our data. For pre-processing, we made our data frame taking a certain number of sequences and used it for training and testing. We used 2D CNN model for the M files to compress the size of the file and capture the spatial features of this data appropriately. We decided to add all the frames into one 384 by 88 frame, resulting in a heat map image of multiple paws showing the strides or walk, and then fed it to the CNN. We chose to use an LSTM model because of the temporal nature of the G file. Data was divided into sequences of 120 frames, each having 4 percentage force columns, and gave it to a 3-layer LSTM model as shown. We added dropout layers to take care of overfitting. Now let's take a look at the model evaluations. The baseline random forest model performs slightly better than random guessing, giving us an F1 score of around 57% and accuracy of around 58%. The LSTM model was trained for the following hyperparameters: 10 epochs, batch size of 32, and window size of 120. It performs significantly better than the baseline, giving us F1 score of around 95% and accuracy of around 93%. Let's take a look at the future work. Because we had less M files to work with, our CNN architecture didn't perform well compared to RNN. But in the future, there is scope to train a CNN on more files and combine the CNN and RNN architectures with an MLP to learn both spatial and temporal features and give us better results. Thank you.